Okay, we have a few notes I want to take today. That's it, just a few notes, kind of get us back in the swing of things here. Just kind of wrap up the stuff about ellipses and whatnot, circles. So we're going to do that. One example I kind of gave you on Friday, talk about, you know, the argument me and my father had. It was an actual true story, so we're going to try to finish that problem up. I'm guessing at the numbers for the bridge. I know the truck numbers, but the bridge numbers I'm a little concerned about. But yeah, so we're gonna talk about that problem, and then next we're gonna go into the next section, which is unit 9.3, which is hyperbolas. So we're gonna just do a light introduction today, what a hyperbola is, see the differences, look at the formula basically today. We won't do anything really too far in depth with that. We'll just kind of do a real basic introduction. So that's what we're looking at today. So yeah, so that's what we're gonna be covering. Later this week we'll probably have an assignment on this stuff, either tomorrow or Wednesday, and then hopefully I'm either back Wednesday or Thursday this week, and then we'll continue with notes. Semester test, I know that every class has a semester test coming up. Mine will be after break, after winter break. I know that's not convenient, but I haven't been there a lot, so I'm gonna make sure that it's after winter break. It's like the Tuesday after we get back. So because I know you have quite a few semester tests coming up this week and next week, so I didn't want to just throw mine in the loop and you guys aren't ready because I haven't been there. So we'll probably start reviewing when I get back, so either Thursday, probably Thursday I'll start reviewing, because I think I'm back Thursday for sure. So but I could be back Wednesday, who knows, hope. But yeah, so that's kind of the idea. We'll start reviewing on Thursday this week. You'll get a physical copy of the practice guide for the semester test in hand, and that way by next, you know, the Tuesday after winter break, hopefully you'll be ready. You can watch the videos over and over and over to make sure you're familiar with it and you're not getting lost and whatnot. And so I didn't want to put it before break. It's only going to be worth 10%. I think in the beginning of the year I said 20, but with me being gone, I'm going to lower that percentage down, so it's going to be significantly less, you know. So don't fear that, you know, that semester test grade is going to wreck you. It shouldn't. So, all right, yeah, we're going to do a few notes here, kind of see what you guys have, and we'll get going here. Is there any questions before we begin today?
Brittany just came in with a pass.
Perfect. Yeah, so, you know, yep, I figured as much.
Everyone ready to go? Alright, they're ready.
Okay, alright. So yeah, so let's start talking about ellipses, circles, whatnot. Just remember, an ellipse or a circle, no matter what type it is, let's say it's a vertical ellipse where it's going more up and down. Let's say that, you know, here's my center, and we're going to go up and down maybe 4 from there, up and down 4, 1, 2, 3, 4, and then maybe right and left 1, that type of thing. So the ellipse itself is a vertical ellipse. Now, what we talked about last week was where the major axis would be. The major axis is the longer distance. So in this case, the longer number would be right and left. The longer distance would be up and down. So that would be below the y number. So just to give you an idea, I can like reverse engineer this problem and write down the formula for it. So it looks like my center on this particular problem is 1, 2, 3, 4, 5, 6. So it's -6 on the x-axis. Right? So x plus 6 will represent -6. And then on the y, 1, 2, 3, 4, 5, it's up 5. So we'll put a -5 here. And that should be a y, not an x. Y -5. There we go. And that would represent +5 on the y-axis. Now the right and left motion is only 1, so when you square it, that number goes here. And then the up and down motion is 4, and when you square that, that would be a 16. So 4 squared would be 16. So that's where my numbers come from. So I can reverse engineer the problem. By looking at the graph, I can give you the formula super quickly. So that's something I want you to be aware of. All right. But again, the reason why I bring this problem up is just before we get started with that, you know, that simple problem about my father and my argument. This one, I just want you to be able to see, you know, what a vertical, you know, ellipse would look like. The major axis is the 16 in this case, as opposed to the minor axis, which is 1. So I know some people got confused by that last week. So grades will be updated tonight, so just be aware of that. Everything will be in the grade book tonight, and so tomorrow you can kind of see if you're missing anything. You can get it turned in the next week or so. Okay. But yeah, let's jump right in. Let's talk about that one problem. I just wanted to let you see a vertical. I didn't do one last Friday. I felt kind of bad, so there you go. Alright, so here's the problem that I kind of that I talked about. I kind of filled in some of my numbers here and typed it out so it's a little bit easier to see. So a semi is intending to drive through a symmetrical tunnel. So the tunnel for mine was circular. I said it was 20 by 20. I don't know the exact dimensions of it. It's above 13.5 because tunnels are usually above that, but I'm just going to put 20. I think it was a little bit less than that. But if the semi stays on their side of the street, would they actually fit into the archway? So let me just draw what we were talking about. So here is that archway that my father was intending to drive through. They said he couldn't fit. The distance up and down is 20 feet. So that was the height of the bridge, the tunnel that you're going through. The distance across was also 20. So I know this is not drawn to scale, but this was also 20 feet. And the semi-truck that was going underneath it. Now I'm going to draw the back of the semi like it's driving into the actual into the tunnel. The semi-truck itself is 9 feet wide. So 9 feet wide, that is the distance from here to here. And the truck itself is 13.5 feet tall. 13.5 feet tall from like tire to the top of the truck. And the argument me and my father had, a legitimate argument, was would we fit? And my father proceeded to tell me that we wouldn't, even if we stayed on that side of the road or not. I said we would. You might have to drive down the middle of the road, and he argued that you can't do that. He's a professional, he can't do that. So this is the argument we had, and I want to talk about the mathematics. Would we actually fit? You know, would my argument still stand? So let's kind of go through the math here. So I'm gonna create the formula like I just did in that last problem, where I have a center. I'm gonna call the center of this particular problem 0, 0. So this is gonna be my 0, 0. Okay. And then I have a right and left motion, an up and down motion for the actual ellipse itself. So the center is at 0, 0. So this would be the formula that's representing it. Again, the reason why I picked 0, 0, that's just the center. I don't have to worry about, going left 5 and up 10. I don't need to worry about that if we're just establishing where the middle of the tunnel is. Now, the right and left motion, the up motion is 20. So that is this vertical motion. This is 20 going from here up. So that is the vertical number. So we have to square that number. Okay, so that's 20 squared, that's the vertical, it's on the y-axis. The right and left motion, the A number, in this case, that's my generic number I always use. This number going from here to here is 10. So we have to square that number. Again, it's from the center to the outside. That's how we use those numbers. So hopefully those numbers make sense. Alright, now I'm going to square those numbers and I'll take a little break. I know I'm going kind of quick here for you, sorry. Get in that mode where I just start going. So we have x squared over 100 and y squared over 400. Okay, I'll stop there. So. You guys just let me know when you guys are ready.
Does anybody need more time for it? Alrighty.
Okay, so there's two things I want to talk about with this problem. Is number one, if my father stayed on his side of the road, would the semi clip the top of the bridge? Okay, because if we can answer that, if the semi will fit, then we don't need to check the one where going down the middle of the road. So I'm really putting this thing to the test. Will it clip? And what I'm worried about is will it hit in this general area? Will the top corner hit? Because obviously the clearance to the top of my theoretical arc here is 20 feet, so that's well above the 13.5 feet of my semi. I'm just worried about the corner, when I clip the corner of the semi. So what we need to do here is plug in my numbers. So from the center, so imagine, because how semis work, how if you're not familiar with it, if your parents never drove a semi, or if you don't know anyone that does, they're always trained to drive on so that their tires on the middle line. So that way they never have to worry about crossing the line, they're always on it. That's why when you drive down the road, sometimes the semis seem like they're really close to you. They're trained to have that left wheel here right on the line, so they know that they'll be safe on the other side of the road. They don't have to worry about both sides. They don't try to drive down the middle. They just hug the one line. So that way that they're always good. They're always in the middle of their lane. So all I have to worry about is just going over 9 feet this way. So what I'm going to do is I'm going to plug in 9 into my X, because that's the horizontal number, right? I'm going to plug in 9 into my X. And what I want to find is if I plug in 9 here into X, I plug a 9 in here, so 9 squared, 9 feet. All I need to do is solve for Y. So this is like an old school problem where you just solve for Y. You do your algebra, and we solve for Y by taking square roots and whatnot. And what I'm looking for is the height. Is my Y number going to be above 13.5 feet? Will it be above that number? If it's above, then we're safe. Because what this formula gives me is the height where the bridge is at that exact moment. So at 9 feet over, will it be above the semi? I'm looking for it to be above 13.5. Hopefully that makes sense to you. Okay, so let's go through some of the numbers here. So I'm going to square my numbers. So we're going to need maybe some calculators. So if you need to get yours out, maybe do that right now. I think Miss Scott's got a couple on her desk there. I think I even have some behind her in my office. But let's do a couple numbers here. So 9 squared is 81. The Y squared, I'm going to leave it alone. The 400 and the 1. Okay, so to solve this thing out, I'm going to erase a little bit. We don't need this extra side of the bridge. Okay, I'm going to move the 81 over 100 over. So I'm moving this over, and it will subtract. Now, how you subtract fractions. I'm going to make the number 1 100 over 100. Because that's the number 1. 100 divided by 100 is 1. And I'm going to subtract the 81 over 100. Okay, let me write the 1. Come on, iPad. Alright, now I definitively know that it is not me. It is definitely the iPad doing this. Oh my goodness. I just got a new iPad. That's why I say that. This is a brand new iPad. So, alright. Not me. Stupid iPads. Now don't even let me erase it. Oh my gosh. Alright. Anyway, 100 minus 81. What is that? 19 over 100? If I subtract that? Can't subtract. Somebody confirm that for me. I can do all this crazy math, but I can't subtract. Alright. Okay. Anyway. So we've moved that number over. We got to this point. I'm going to multiply the 400 across. So if I multiply this 400 across, this will work out to be a number. So 19 over 100. I'm going to multiply by 400. So how you do this, how you multiply by a constant, you take the number times the top and divide by the bottom. So 400 times 19, and then you divide by 100. And this works out to be 76. Okay, so now, what do I need to do next? What can you guys tell me?
Find the square root.
Square root, good. We do the square root of 76. So the square root of 76 is 8.71. Now, what does this number mean?
You said it can't make it through.
Yeah. My father was right on that account. The semi will most definitely clip that bridge at that moment. The height of the bridge at 9 feet over from the center is about 8.5 feet tall. Okay, so he was right in that regard. Still makes me mad. Now, let's check my theory. What happens if we drove down the middle of the road? So if we drove down the middle, because that was my theory, like, hey Dad, just go down the middle of the road, you'll fit. Okay, so let's do that. Let's drive down the middle of the road and see how that affects my number. So the only difference I have to do here, and I'm gonna try to do this as quick as I can, because obviously we've already checked and my father was right in the first check. Still doesn't make me happy that he was right. So the check is, if I drove down the middle of the road, right? So let me take a screenshot of that. I don't want to erase anything here. Okay, so if I drove down the middle of the road, what the only difference would be, this 9 would change here, right? This 9 would change because I'm not going 9 feet over. And these numbers over here would change. Okay, so instead of going 9 feet over, I'm going to put the semi in the middle of the road, which is illegal. That's, my father kind of reminded me of that. So if I put it in the middle of the road, how far over would I be if this truck was slid this direction?
4.5?
Yeah, 4.5 feet. It'll be 4.5 feet on the right side of the road, 4.5 feet on the left. Again, illegal. You're not supposed to drive down the middle. You're not supposed to play Pac-Man. So you have 4.5 feet on the right, 4.5 feet on the left. My theory was you'd still fit, right? So I'm going to plug 4.5 in here and square it. So instead of 9, 4.5. So 4.5 squared. So 4.5 squared. It's 20.25, right? That's squaring it, not quite 81, right? So we're getting 20.25. We're going to subtract that 20.25 over, if it allows me to write it. 20. Oh, come on, iPad, come on. 20.25. All right, and then we're going to subtract it from the 100. So 100 minus the 20.25, I get 79.75, because that's the 100 minus the 20.25. And then I took it times 400, so 79.75. Took that times 400 and then divided by 100. And I get 319.
Everyone clear what he's doing there? Everyone's good?
Okay.
Alright.
We take the square root of that number. So square root of 319. So square root of 319. And I get 17.86 feet. So, in theory, we were both right. Right, my father was right. He can't drive down the middle of the road. He can't drive.
Get that.
Shut up, Siri. All right. So, my father was right. He can't drive down his side of the road. But I was also correct that if we drove down the middle, we would be fine. We would miss it by 3 feet. Better safe than sorry. You know, that's going off of the, just thinking about it a little more, smart. My father's probably correct in all general, forms, because obviously you don't want to risk that. Because if you hit a bridge, you have to pay for the damages on it. So you don't want to buy a bridge that way. But in my defense, my math was right. We would have fit. I tried to prove my argument. We had a pretty lengthy argument about it. I think we would still fit. I think I used the number 18 feet, and I think you'd still fit. You'd fit by like a half a foot or something like that. Now again, this really comes down to the inflation of your tire. So if my tire was a little bit lower, you know, the semi would be lower to the ground. It depends if there's any, you know, dirt and debris on the ground itself, because that would raise the truck up, and if there's any bounces, you'd bounce into the bridge. That would be not a good thing. So you have to be very careful. But yeah, we were right in both accounts. My father was right, and I was right at one point. He's probably more right. It still makes me mad. All right, there you go. Real life problem. Questions though.
Everyone good on that one? That was good.
Okay, so let's get to the new stuff today. New stuff today, we have to do a hyperbola today. So this is a brand new topic. It's an introduction day. It's nothing like crazy in depth. I just want to intro it so you kind of know what these are, what to do. Let's talk about what a hyperbola is first, and then we'll talk about, you know, the formula itself and the graph. So hyperbola, if you take a conic section, so take a cone, and imagine that there is another cone on the other side of it. Okay, perfectly like symmetrical, one on top, one on the bottom. And you were to take a flat surface, a plane, and cut through it. Cut through it. What it would do to the cones, it would score both cones, so it would score them and cut them, and you're kind of seeing what I'm drawing here. It's kind of tough to see this, but what would happen is that if you were to look at the cones from the front, like this is what it would appear to do to your cones. There would be a cut out of the front of the cone, and on the bottom, the same exact cut. That's what your cones would look like. They'd be symmetrical, but there'd be a cut in the front and the back. So you're taking like a bandsaw and cutting straight through them. It would be very similar to a parabola, but there'd be two. There'd be one on the top, one on the bottom. So that's a hyperbola. It's different than a parabola in the sense that you're going straight up and down, as opposed to cutting at an angle. A parabola is cut at an angle, so this plane would be, now I'm going to draw this and I'll erase it here in a second. The plane for a parabola would be going more this way, like kind of tilted, as opposed to a hyperbola, which is like almost perpendicular. It means 90 degrees, right? Straight up and down. So that's what a hyperbola is. So if you want to know where it comes from on a conic section. Now, let's discuss what we need to do here. The hyperbola is, in all sense of the terms, this is the one that, you know, satellite dishes use. You know, a parabola is really close. It does. You know, a parabola really resembles a satellite dish in theory, but the hyperbola is the one they actually use. So, it's the main form. It has a focus in it. It has, you know, a couple what they call asymptotes, where there's a couple of boundaries where you're not allowed to cross. So yeah, it's kind of a weird topic, but I'm gonna kind of show you the formula and show you the generics here. But let's take a look at the graph. So other than, you know, these pictures of these conic sections, let's take a look at what the formula actually looks like. Okay. All right. So let's take a look. So I'm going to draw this pretty plain here, just so you guys can see this. If it allows me to draw that second one, there we go. All right. And this parabola is going up this way, and this parabola is going this way, and there's another one going the other direction. This is a hyperbola. It's a horizontal one. It's going right and left. It's got a focus on the inside. So there's two foci in this particular case. There's a, no, I'll just kind of draw this out here. There's a focus on the inside, like kind of over here, in this general area. You know, I'm just kind of making up a number where they go. There's a focus, so there's a focus and a focus. And then how they're actually drawn is that there is what I called an asymptote, where there's this weird undefined boundary that goes right through the center of your graph. wherever your graph's centered at. So if we move the graph around, these are called asymptotes. So let me spell this out. Silent P on the inside. So they're points of undefined boundaries where you can't cross them. I think in Algebra 2 they talked about it. Bless you, Miss Scott. All right. Yeah, these asymptotes are, you can't cross them, so the actual hyperbola would hug up against it. So this green arrow here, I didn't draw it really to scale. This green arrow would actually come like and go really close up against it, going in that general direction. Should be going this way, and same with the others. So, so again, like over here, this thing would go really close, like infinitely close up to it, but never actually cross it. That's a hyperbola. Now I want to show you the formula today, because obviously you're seeing the graph of it, but I want to show you the generic formula for it, just so you get the sense for how it works, how to find the foci. That's just to intro it today. I just want to do one of these. So, all right, do we understand what we're going to be looking at?
Everyone good? Yeah.
Okay, so let's just take a look at a generic formula. Then we're going to go take a look at the picture of this thing here in a second. So I'm just going to give you an example, and then we're going to use it, okay? So here it is. So let's say x, my wrist is really activating the screen here, x plus 3 squared, y minus 2 squared, and let's put some numbers on the bottom, and there is a minus sign in between them. That is the difference between a hyperbola and an ellipse. There's a minus sign. So this right here gives it away that is a hyperbola, because it looks almost hyperbola. There we go. It looks almost like an ellipse. The only difference is the minus sign. Now the numbers. Let's go with 25, and let's go with 36. Yes.
As soon as you started writing the word hyperbola, your video and audio froze.
Ooh, interesting. How's that? Is that back? Can you guys hear? Are we good? Can you guys hear me?
Yes.
Yeah,
Yep.
okay. Okay, good. Sorry. All right. So yeah, so we'll continue here with this. All right, we'll continue and we'll talk about how to do this particular problem. So it looks just like the ellipse formula. It almost has the same look, just as a minus sign. Now the only difference here is that it's how it's drawn, right? It's not going together, it's kind of bowing outwards. In this particular case, it doesn't matter which number is larger on the bottom. I know like on an ellipse, we always compare the two bottom numbers, right? You always compare the bottom and you figure out where the major axis is. We don't have to worry about that on a hyperbola, okay? On a hyperbola, and I'll show you different examples of this tomorrow, you just look at the one in the front, just this one. So the letters like X and Y could be switched around. They could, like the Y could be in the front, but you only look at the front number, and this is called the transverse axis. It's not the major axis because you don't have to worry about a major and a minor. It's just there's one axis you travel along, so it's called the transverse axis. A little bit different. That's the only difference here. All right, but we're going to draw this. That's what we're going to look at. We're going to look at the very basics here. Yes.
Your audio froze, just the audio. So can you explain about the transverse axis again?
Yeah. All right. So there, like on an ellipse, there's two axes, right? There's the major and minor. But on a hyperbola, there's only one. You just use the number in the front. The X and Y could switch places. So I could have, this Y could be technically up here, and it would still be, a very similar looking problem. You only use the number in the front, the bottom number. I don't care which number is larger, just the front number. And that's called the transverse axis. It's kind of like a major axis, the distance you're traveling. Do you guys hear that just fine?
Yep.
Okay, let's go draw this thing. So we can get our one example today, and then we'll call it a day here. So we have x plus 3 squared over 25, minus y minus 2 squared over 36 equals 1. The center is still found the exact same way, the center of my hyperbola. So where's the center going to be on this one?
You're going to say it a little louder. -3, +2.
Good. -3, 2. Alright, so yeah, it's still the same work. -3 over 2 up in the air. Alright, so that's the center still. Okay, now this is the difference. On this problem, you just use the number out front. You're using just this block to tell which direction I'm going. So the letter on the top says X, right? The X is the front one. So I'm going right and left. This is a horizontal hyperbola, because the X is out front. If the Y was out front, it'd be a vertical. That's the difference between a hyperbola and an ellipse. These are actually easier to understand. So we're going right and left on this one because it's horizontal. The X is the front number. And you just take the square root of that bottom number. So the square root of 25, you're going to go 5 right and left because the X is the front number. Again, this tells you which direction you're going. So I'm going right and left 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And now the next part is you have to figure out where the asymptotes go. You know, where the undefined boundary are, so I can figure out how to draw the satellite dishes, right? The actual branches, if you will, where you draw the actual hyperbolas. So the asymptotes. This is where you're going to use a generic formula for a line. A line is like y equals mx plus b, right? So y equals mx plus b. And you're going to use the center as your b number, so I don't need to put that in there. But for the slope, this m, you're going to use the numbers on the bottom of your fractions. So you're going to use that 36 and the 25, and we're going to take the square root of those. So it's kind of like the major minor axis idea again. Now, how this works is how slope works is it's always rise over run, right? That's how slope works in generic like algebra 1 terms. So for us, which number up here would represent rising out of these two? Which one would represent rise? What do you guys think? Did somebody say something there? I couldn't hear it. What would represent rise? X's or Y's?
Yep, he's asking you guys which number on here is rise. The Y?
Yeah, the Y number. So, what is the square root of the number that's below the Y? Square root of 36 is 6, thank you. And the square root of the number below X, that's your run number, right? X's are always runs. Square root of 25 is?
5.
5. Alright, and there's my slope. So this is how I draw my asymptotes. I'm going to use that as my slope from the center. So I'm going to go up 6, rise 6, 1, 2, 3, 4, 5, 6, and run 5. 1, 2, 3, 4, 5. And then do it again. I can even go back. You know, the same thing. 1, 2, 3, 4, 5, 6, and back 5. And I can see this is where my asymptote is going to go. And then how I get the other one, you just change it to negative. I drop 6, run 5. Or go up 6 and back 5. Again, I'm using that 6 and 5 idea. And it draws two different ones, positive or negative. And now I can draw the branches. Now I can figure out where my hyperbola will go. It'll go up and hug up against this. It'll hug up against that. Same thing over here. Does everyone understand the generics here?
Good on this one?
Okay, that's my last problem of the day. I just wanted you to get that kind of written down here. So that's our last one. So if you can get your notes finished up, you're good for the day. We're going to look at a couple more of these tomorrow because obviously today was the intro day. So don't feel like, oh my gosh, I'm totally lost. It's the first day. We're going to do a ton more of these next couple days. So don't feel like you're lost yet. I just want to intro what we're doing. Okay. Thank you, Ms. Scott. I'll see you here in a few minutes for the next class. Remember, tonight grades will be updated in JMC. I'll be putting in everything from Google Classroom so you can kind of see what you need to get corrected and fixed, all that good stuff. Semester test will be after winter break. It'll be the Tuesday after winter break. So.
Still talking.
All right. Thanks, guys.
Thank you.